Right, we're going to look now at the Friedel Crafts alkylation reaction, and that's when we use an alkyl halide in the presence of a Lewis acid to put an alkyl group on a benzene ring. And before we do that, we'll have to have a bit of a refresher on the stability of carbocations. First of all, let's remind ourselves what our primary, secondary, and tertiary halide looks like. And if X is a halogen atom, then primary will have the halogen on the end of the chain, secondary has it somewhere in the middle, and tertiary has 3 carbons connected to the C that has the actual halogen group attached to it. When you remove the halogen group, you end up with a carbocation, and that's what we've got here. And the carbocation is a C+, and you can see that the stability of the C+ is going to be dependent on the kind of carbocation it is, be it tertiary, secondary, or primary. The most stable C+ is the tertiary C+. That's the one where the C+ has 3 methyls or 3 carbon groups attached to it. Now what happens here with the tertiary carbocation is that it's subject to a phenomenon called hyperconjugation, where the electrons in these CH bonds can stabilize the C+. Now this is only possible in a tertiary and a secondary system. We can get hyperconjugation going here. We can obviously get more hyperconjugation in the tertiary system than we can with the secondary system, but you'll notice that these bonds directly to the hydrogens are incapable of actually stabilizing that positive charge. So this is used to explain why the tertiary C+ is more stable than secondary, is more stable than primary. Alright, so let's go ahead and take a look at a couple of examples. I'll start off with a secondary alkyl halide, and we'll see what kind of reaction that undergoes. Alright, so the example I'm going to use will be this one. And we're going to use this as our halide. And this one is secondary. But as well as the halide, we also need a Lewis acid, and this will help to remove the halide from the secondary halide. Alright, let's have a look at how that works. We've got our Lewis acid, and now we've got our alkyl halide, and this is pretty similar to the bromination process we looked at earlier. The Lewis acid acts in a similar fashion. What it does is it has no electrons here, so it doesn't have a complete octet. So what it will do is it will react with this in this fashion, and we'll get AlCl4- and our alkyl halide. Now just be careful here when you're doing this reaction. What it's doing is it's forming a bond between the Al and the Cl, but it's using the electrons from the Cl and C bond to do that. That leaves the C short of an electron. That's how it becomes positively charged. But we use both electrons here to fill up the aluminum's octet, and that's how this Lewis acid will interact with the halide to give this carbocation. The carbocation then will react with the benzene ring. Now, before we do that, let me sort of give you an idea about the stability here. This is a secondary carbocation, and there is no possibility for this secondary carbocation to rearrange into anything more stable than what it is. So the only possibility that we're going to have here will be for reaction with this carbocation. In a little bit, I will give you an example of a process where we do end up seeing a carbocation rearrangement, but that's only because a more stable carbocation was possible in those instances. Here, this will be the only one. Alright, so what's going to happen is it's going to react with the benzene ring, and it reacts in the same way as we've seen these other electrophiles react. Alright, so that leaves a positive charge here, and the alkyl group is now bonded to the benzene ring. And then we can lose H plus and reform the aromatic system. So this reaction gives just this single product, and that's this one here, and no other alkyl benzene products are formed. Alright, so just in summary, what we're looking at here is a secondary carbocation that cannot rearrange into anything more stable, so we end up getting just this alkyl benzene product.